Here we have Antonio Fernandez. Will talk to us about nowcasting temporal trends using indirect surveys. So I'll pass you over. Thank you very much.
Okay. Thanks. As you see, this is joint work with researchers from USC, India Networks, which is where I am, and UC3M, Universidad Carlos III de Madrid. The presentation is going to be a little less fundamental, I would say. It's going to be more like an overview of a project that we've been developing for a few years. It all started in March 2020. Probably many of you will remember the dates. This is the front page of the biggest newspaper in Spain. And although it's Spanish, it should be easy to translate. Essentially saying that we had more than 3,000 cases of COVID officially in March 13th. One day later, and after all the backlog of reporting, the official the official data as of now, the official number as of now is that on March 14th, 2020, there were 6,400 cases. Of course, these were only the cases that were confirmed with a proper test, PCR at the time. So what happened is that we asked ourselves, how close is this number to the actual number of cases? So keeping in mind this number, like 6,400 cases officially, what we did is on March 13th, we launched in Twitter for 24 hours a survey asking people how many of your acquaintances or friends have symptoms or have COVID-19. As you see, I got 732 answers, which in total, by only considering that those who reported 1, 2, or 3 or more here, they were reporting at least 374 cases. The problem is that we had to translate that into an estimate of how many people were sick. So for that, we assumed that everybody knew 50 people, which is one of the Dunbar numbers. Dunbar is a sociologist that has estimated how many people usually somebody, like an average person, has contact with. And he has like different rings or different levels, starting from your family, which is typical of size 5, family and friends, which is size 10 to 15, friends, and acquaintances, which is roughly like 50, and then your wider network, which is roughly 150. And if you know somebody, that means that you're going to be dropping somebody from one of these circles. So these are quite stable numbers. So assuming 50 friends, our estimate was that on March 14th in Spain, there were almost 500,000 cases, which is like roughly 1% of the population. How good was this? Well, we looked at 2 weeks later and taking into account that the case fatality ratio measured in China was a little bit above 1%, and that from infection to fatality, the average delay was 2 weeks, and that there were roughly 6,000 fatalities reported those 2 weeks down the river. The estimate is that on that date, roughly the number of cases were about 430,000, which is almost like 1% of the population. So we moved this to a bigger survey that has been deployed for more than 4 years now. It's still collecting data, in which we ask people, how many people you know and how many of them have or had COVID. This type of questions is what is called aggregated relational data, and it's data collected from indirect questions. What is good about these type of surveys is that they are more privacy preserving than a direct survey. If you ask somebody whether they have a given stigma, they may not answer clearly, while if you're asking how many people they know who had that particular stigma, they may be a little bit more open to report that. Each response reports more than one person, unlike direct surveys in which you are asking for one person's state. And on the negative side, responses can be biased. Somebody may not know the state of a person in their circle. They may not remember them, or they may on purpose lie. These are things that can happen. The classical way of using this aggregational relational data is to estimate a given parameter, like the prevalence of COVID or the prevalence of AIDS, which is one of the applications that is being used now, is using an algorithm that is called, or a technique, statistical technique that is called network scale-up method, or NSUM. The idea, like for instance, this is one of the versions of the NSUM. The idea is that for every person that you ask, every V in your sample, you estimate what is the ratio between their acquaintances and the number of cases they report, and you just do the mean of that value, and that is your estimate of the prevalence. So these techniques, ARD and NSUM, has been used already for more than 30 years. In fact, there is a paper that was published 2 years ago with that title, the 30 years of the NSUM method. And it started being used to estimate fatalities or casualties in an earthquake in Mexico City. But it's usually quite useful in environments in which it is hard to reach the population that you are trying to estimate, you are trying to sample. So for instance, female sex workers, prevalence of drug abuse, prevalence of HIV, or prevalence of COVID-19. These techniques are good techniques to do what we call nowcasting, which is estimate what is the current value of a particular presence in a population of what we call a hidden population. However, as far as we know, it was not really used taking these surveys over time. Most of these surveys that I'm showing here are in fact done using paper. Like they go to a house, to a city, to a neighborhood. They deploy people that they collect the survey responses, and they go to the lab and they just analyze that response in a one-time shot thing. What we want to explore in this work I'm presenting today is what if we continuously monitor the population and run these surveys over and over time, whether we can track the evolution of a particular phenomenon. In particular, the one that we center our experiments on was COVID-19, but that was just because availability of data. So just to give you an idea, how good are these estimates? What I'm showing here, this is still a one-time shot, but we ran our survey since March to April. So we collected 1,000 responses in Spain, and we compare the estimates of the prevalence, like how many people, not prevalence, seropositivity, sorry. How many people had COVID since the very beginning until early May in Spain, in the different regions. And we compare that with a serology study that was done by the Ministry of Health, in which they tested 60,000 people for antibodies of COVID. As you see, we use 1,000 responses versus 60,000. And as you see, our estimates of the percentage of the population that had antibodies is actually quite good. In particular, it has a huge correlation, more than 0.9. So in this particular work that I'm presenting today, as I said, we are moving from the static scenario in which we deploy a survey, indirect survey, we collect the responses to the survey, and we try to estimate what is the situation today, to a scenario in which we keep deploying surveys periodically, and we collect that continuously. So we're going to have the network, the social network, because as you see, when I ask somebody from an indirect question, there is an underlying network, which is the social network of that particular person, is how, which are the contacts or the circle of friends and acquaintances of which this person is reporting. So this graph can change over time. And in particular, we're looking essentially at the prevalence. If you want, you can look at it as a special case of a color graph, in which you have like the general population who is healthy and the population who's infected with COVID-19 or any other phenomenon that you're trying to measure. So we're gonna define this dynamic graph formulation to estimate the prevalence, in particular COVID-19, but it could be something else. What we show is that it is possible to look at how the prevalence evolves. So we are not going to be so worried about estimating the exact value of the prevalence, but we're going to be more interested in identifying whether the prevalence goes up or down. Essentially, it's kind of like, looking at the first derivative. We are going to show also that with the same number of people surveyed, you can get a better estimate if you use indirect questions. Moreover, if you apply a smoothing by just doing a moving average of these indirect estimates, you can do better than just taking estimates every day one by one. And finally, I'll show some actual results with simulations and real data. So as I said, we have this model of a dynamic graph or a time evolving graph, if you want, in which we have a population n, which are the nodes of the graph, and then at every time t, the graph can have an arbitrary topology and it has an infected population. If you want, what you have is a color graph in which blue nodes are healthy and the red nodes are sick, are infected. The prevalence, which is what we want to estimate for a given graph GT at time t, is the size of the hidden population, the infected population, versus the overall size of the graph. For simplicity, we assume that n is always the same set. And what changes over time, as I said, is both the edges of the directed graph and the coloring of the graph. In general, an edge from a node to another node is saying that an edge from V to U is saying that U knows what is the state, the color of U. U knows the color of V and is willing to report it if asked. So we made a couple of assumptions in order to get some of the results. The first one is that although, as I was saying, the graphs GT change over time, we will assume that they have the same mean of the degree and the same variance. So the degree of both graphs, the in degree, doesn't change from one graph to the other. If it changes a little bit, in essence, the results will not change drastically. But this is kind of supported by these Dunbar studies that I was mentioning before. Essentially, your group of friends is always roughly the same size. Then we also assume that if the probability of a given node that is an in-neighbor of U, node V that is an in-neighbor of U, the probability that this node V belongs to the hidden population or this infected population doesn't depend on the degree of U. So this is oblivious to the degree of the neighbor. So with this, I'm going to show essentially three big results. For that, I'm going to describe how do we sample, essentially how do we run or how we model the process of sampling using indirect surveys. Essentially, what we do is we select a node U at time t from the graph GT uniformly at random, and we have a random variable xt, which is the number of infected neighbors that U is reporting. In a real situation, we will not select only U, we will select a subset of nodes, S, uniformly at random. And if since that makes things simpler, we assume that we select them with replacement, just for simplicity. So essentially, in this particular case, U will report xt equal to 1 because he only has one neighbor who belongs to the hidden population who's infected. The first theorem, or the first result, is that with these assumptions that we made, essentially the two assumptions in which the in degree doesn't affect the probability that a node, the in degree of U doesn't affect the probability that a node V in its in neighborhood is infected or not, and the fact that we estimate that the degree of the average degree over the whole graph is constant, we can prove that the expectation of xt is actually the parameter that we want to estimate times the average degree. This is nice because if we are looking into the trend, we don't care so much about the actual value of ft, but we want to know whether ft grows or decreases or stays the same. Then just by estimating the expectation of xt, by sampling and using the mean as estimator, we can capture that phenomenon. If we really need to know the value of ft, then we need to estimate mu. And for that, one thing that can be done is like look at one particular time t in which the actual prevalence is known, and that will allow us to estimate mu with certain error, but still it will help to get an evolution, the evolution of the prevalence over time. So the second theorem has to do with under which situation or under which conditions indirect questions or indirect reporting is actually better than direct reporting. So we assume that we have a sample S, which is large enough, and we have Y is telling us what's the mean of what is the estimation that we get from direct sampling, and xt is the one that we get from indirect sampling. So what we show is if the variance of the graph, the network, as I said, we assumed that the variance remains stable over time. If that variance is smaller than a certain constant that you see value, then we do have that the probability that the error that we're making with an indirect survey is larger than lambda is in fact smaller than the error that we make with the direct survey is larger than the same lambda. That means that if the variance of the network is not large, small, then indirect surveys are better than direct surveys. This result has influenced us to, now I will mention that at the end, but we've been running some real experiments, deploying actual surveys, and we've been trying to maintain this variance small by asking questions in which we directly tell the participants to consider only a small set of potential friends to be considered. The only parameter that is a little bit peculiar is phi of t. Phi of t is trying to represent the probability of co-infection. Essentially, what is the probability that V prime in that figure on the right? What is the probability that V prime is infected, conditioned to the fact that V is already infected? If they are completely independent events, then phi of t will be equal to f of t. But it could happen that the fact that V is infected means that V prime cannot be infected, or vice versa. V infected means that very likely V prime is also infected, in which case we are the other extremes, which is phi of t equals 0 or phi of t equal 1. In any case, the bottom line here is that for the same sample size, if the variance of the degree is not too large, then what we find is that the indirect surveys can do better estimates than direct. Then the third result we're showing has to do with, what happens if we apply smoothing. What we are assuming, or what we use for this result, is that the evolution of the prevalence is not too fast. Essentially, there are no drastic changes from one day to the next, which is, what happens usually in phenomena like epidemics. It's not like, you have half the population infected one day and 1% the next day or something like that. And also we assume that the standard deviation of the variable xt, the variation of the variance of the variable xt is also not too large. So we assume that they change slowly over time. And what you see on the right is the actual data that we have from the COVID cases in California. As you see, the epsilon for F in the plot in the center is about 1/100, 10 to the minus 2, while the epsilon sigma in the second one is no more than 1/10. So they are reasonably small values. So with this in mind, what we show is that if instead of using as estimator the estimator from indirect survey that we will obtain in a given day, which is what we call x of t, instead of that, we use the average over a window of 2w plus 1 days, we get that our estimate is better if if lambda is larger than this expression, which essentially tells us that if the epsilon f and epsilon sigma are small enough, and the ratio essentially, nt divided by nw, nt is the number of samples at a certain time, nw is the number of samples in the whole window. So as long as this is small, nt over nw is small, and the epsilons are also small, lambda is small, and this applies to a very large set of cases. So when we go to real data, we have been looking at 3 ways of computing. One is not applying smoothing, applying smoothing in which we take into account how many samples we take every day, and we do an average in which just we take an average of 2W+1 days without looking at how many samples are there. And then we have several options. One is what we compute with indirect surveys, and we compute with direct surveys. And the quality of the result is estimated using or computed using this mean absolute error. So essentially is the error in absolute terms between the ground truth, what we assume is the ground truth, which is in these figures on the right, the blue line with the two infections, and the ones that is estimated. So as you see in the right, the indirect estimates seem to be closer to the blue line than the direct estimates at the bottom, and the estimates in which we take into account the size of the network. We do know the size of the network of every person or every participant in the survey, and we apply ensum as proposed in the classical literature. Here we've been changing the size of the sample. We've been increasing the sample size. There are three Bosch plots. The first three correspond to indirect reporting, the center three to ensum, and the ones on the right have to do with direct estimation. And as you can see, those who are weighted, I mean, the best ones, at least except for n equal 80, actually, I would say in all of them, it's are the indirect reporting estimations, and in particular, the ones in which we do a smoothing. Of course, what happens is like when the sample becomes large, then direct sampling does better and better because it has more data. When we make the window we're looking at, and we increase the window of this interval over which we are smoothing, again, the indirect reporting with smoothing are the ones that behave better until the smoothing is so large that it loses quality. So in this particular case, it seems like the best result is happening with W equal to 4, essentially aggregating 9 values. We also looked at these results with the data obtained by a survey that's been run by Carnegie Mellon using Facebook as the platform of collection. And here they were asking people to report how many in their household has COVID-like symptoms, and how many in their local community had COVID-like symptoms. And these are these two orange and yellow curves that, as you see, are much closer to the official data than the blue line, which is the direct estimate. Looking at a larger number, the previous plot was for California. This is a table in which we look at the biggest states: California, Texas, New York, and Pennsylvania. And what we see is that all the numbers that are in boldface are the ones that give the lowest error. And as you see, they are usually the ones in which we apply indirect estimation at the local community level, and the ones that are underlined are the ones that give the second best, and those are the ones that report how many COVID-like infected they have in their household. So to summarize, we believe that indirect surveys are going to be very useful, and they give a good estimate, and surprisingly, they have not been widely exploited over time and space. Most of the work, I mean, actually, we haven't found any work in which they do like we did in this project. in which we look at the evolution over time of a certain phenomenon by recovering or collecting data periodically using indirect surveys. In the future work, we are putting this to practice. For instance, we are looking at vote intention. We are looking at epidemics. We want to use it for malaria. We plan to do it for other phenomena. But also, I think it would be nice to get the theoretical computer science community to look at this type of graphs. Particular, we are finishing a paper and we look at the worst case behavior of this network scale-up method that has been so widely used, and we show that in fact it can be very bad. And then we are looking at what happens is if the network topology has reasonably good properties. In particular, we look at Erdős-Rényi topologies or power law degree distributions, and the spread or the dissemination of the infected or the hidden population has also nice properties. So this is something that we are looking at the static case, but we want to move into the dynamic case as soon as we can. And I think it's a very interesting area to explore. So thank you. This paper was published in February in AAAI. In fact, it got what would be the second best paper award in one of the tracks. And coronasurveys.org is the project under which all this work has been done since 2020. So the website is there and you can take a look at it. And if you want to contact me for any question, please do so.
Great, thank you very much. Okay, any questions from the Zoom? Is it red? Okay. And any questions?
Yes. First of all, can you go back to the slides? I was trying to write down the title and
oh, sorry.
It's all right. It's all right. And my other question is, so this is not a question about the math. And so on this Dunbar survey or research, I'm not sure what it was. They made this assumption or slight result that 50 people are the number of acquaintances or people that you report based on, if I remember correct.
Okay, initially here, since the survey we were asking didn't have any way to estimate. Essentially, you're telling me, okay, I know 3 persons who have COVID. Okay, but it's 3 out of how many? You could be reporting out of 100 people, or you could be reporting out of 100 people. So in these initial surveys, one way to do it is just use these Dunbar numbers. If you look for Dunbar number in Wikipedia, you'll find information about it. Then in the survey that we later on deployed, we asked explicitly about how many people you are reporting about, which is this RV that I'm showing now. And Zoom, like all these references that I'm providing here, what they do is they do something slightly different. They use a very large survey and they ask questions of which they do know the size of the population they're asking about. Like, for instance, they ask, okay, how many doctors do you know? How many people whose name is Joseph do you know? How many people above 50 years old you know? Since this is data that is known, they essentially using that, a collection of these questions, they get an estimate, or they were estimating the size of your circle of friends, one may say, what they call the ego network. And that's what they use to then apply in this formula that I'm showing there. That's what they use in the RV in there. Anyway, but you wanted the...
No, that partially answered. So my follow-up. But are these surveys have they been done only in Spain or throughout the world?
No, you mean okay, let me see.
I'm curious whether these things vary between countries,
Okay.
the results that you get.
Okay, so this result is only for Spain, but in fact, this survey we ran it. So initially we deployed using. Okay, let me see. This one in Twitter we deployed it in this week of March. So that means like around half of March. We deployed a few of them in Spain, Italy, Greece, Cyprus, UK, Germany, and later France. Then we moved to Google Forms, and that covered many more countries. And finally, in May, we deployed them in our own server, and they have been since then. They were available for the whole world. However, the fact that the survey was open to be answered in the whole world doesn't mean that we got a lot of answers from many countries. So, but yeah, we have answers from some countries. We have more data. From other countries, we have less data. So if you are all the data we collected, it's available in our GitHub. So if you are interested in playing with this data or doing something with it, let me know, or just go directly to the website and coronasurveys.org, and there will be a GitHub link. I think it's on the right bottom, and that sends you to our GitHub. But if you have any problem, just contact me, and I can explain, the data that we have.
Yeah, thank you very much.
Any other questions? And just quickly about this PT, which was like if I roughly understood it, it's how correlated the infections are. Is that right? In the result that says that.
I thought I was sharing my screen and I wasn't.
Yes.
And I was sorry for that.
Okay. Yeah. So you have this result that compares the. There we go. Yeah, and you have this feed, this probability of co-infection. So I guess this is showing you that if the things are the infections are very uncorrelated, then the indirect method is better, which makes sense, I guess, because it's like the people you're friends with are themselves a random sample of the thing. This probably suggests why it works so well with COVID. I guess if you're asking questions, say, trying to estimate drug use, then this would be an example where it's not as good. Would you say that's how I should interpret this, or?
Yeah. Actually, you're right. But it's not independence the best option. The best option is when the probability of so the best is when the probability of co-infection is equal to 1.
Okay.
Because then this becomes 0, right? Oh no, actually the other way around. No.
Yeah.
When the probability of co-infection is almost 0.
Yes. Wait, that's not kind of true.
It's not independence.
Yeah.
Independence would be f of t. So it's less than independence. Yeah, I mean,
does that mean it's negatively correlated? Am I got that wrong?
No, because phi of t is essentially what it says there. That is the probability. Is the probability of v prime being infected conditioned to the fact that v is infected. So it's not a correlation. It's a probability. So it cannot go below 0.
Okay.
So yeah, you're right. Ideally, if the fact that you are infected means that I cannot get infected, that would be the best. In order to have more room for sigma squared for the variance. But in reality, we have some examples in the paper in which we assume that it's independence, and the numbers are quite reasonable. So yeah, we can. I mean, this is satisfied easily. It's not like very difficult to satisfy this property.
Okay. Because presumably it can never really be going to zero, right? Because there's always going to be some problem, unless the thing you're trying to estimate is no instances.
No, I mean honestly, I mean like in cases like COVID, I would say is probably independence is probably not realistic. It's probably higher than f of t. It's more it's closer to 1. But yeah, I mean, I'm sure there must be papers in which they estimate this. I don't think we looked at the literature to find an actual number for this. We should probably.
I see. Okay, thanks a lot. That's great. Thanks to the organisers. Thanks to the speakers.
Let me stop there sharing.
And thanks also to the organisers.
Yeah, thanks.
Well, thanks everybody. Yeah.